alternate forms of derivatives might work, but certainly f of x plus h would make your head spin. Right? Think about if you were trying to derive sine of x, that function, y equals sine of x, and you tried the f of x plus h method, right? You'd have the limit as h approaches 0 of f of x plus h minus f of x all over h. Like, how in God's creation you would be able to manipulate that would be ridiculous. I'd venture to say not doable, but there's probably a way. Josh? That's a different notation for the derivative. D over dx is just the derivative of sine x. With respect to x, which it makes sense because that's the only variable in the function. So the function itself that we're working on is just sine x. And so the derivative of sine x equals is what that is. You're going to see that come up more and more. It was on the bottom of our notes a few days ago, like a few lessons ago, with all the different ways you can write the derivative, like f prime of x or y prime or d dx. There's a whole bunch of different notations just to be familiar with. Stephen? Yes. More, not really yet, but eventually you will in some of the stuff that we get to. Jalen? We haven't gotten there yet, but once we do get to a place where we have to use it, you'll see it. So so with trig, we have just some special rules here, and we start with just the derivative of sine is cosine. That should make sense in some regard, because if you're looking at your sine graph, obviously the slope of it is going to be cyclical as well, right? The slope is probably 1 here, and then it will be 1 again, and then it will be 1 again. As the cycle of sine continues, the slope of it is going to also be on a pattern. And so it makes sense that the derivative of a trig function is also a trig function, something that's cyclical. So the derivative of sine is cosine, and the derivative of cosine is negative sine. So you just have to memorize those. And then on not all exponential functions, but this particular one where the base is e, the derivative of e to the x is e to the x. So we're just going to use these, I guess, rules that people kind of came up with and proved, and find the derivatives of more complicated types of functions. Types of functions, again, that as we get into all these rules, you'll see like the f of x plus h method for any of these would be insane. Wouldn't be really, you wouldn't be able to find the limit. So we have these rules that bypass the need for the f of x plus h. Stephen? Yeah. If you were to kind of use one of those activities that we did, if this is f of x, which is the sine graph, and if you were try to come up with the derivative graph and start evaluating and using that method that we did, what's the slope of our graph at 0? About 1, right? And it is exactly 1. And then if you get to, where's this? Yep, f prime of pi over 2. The slope there we know is 0, right? And these are your cosine values. The cosine of 0 is 1. The cosine of pi over 2 is 0, and so on and so forth. So, yeah, you could expand it out and you would see that. And then you could do the same thing for cosine and realize that it's the opposite of the sine values at those locations. So, jumping into just flat out using them. Finding the derivative of g when it's pi cosine t. So we learned yesterday that if there's a constant out in front, which pi is a constant, that's still going to be out in front. and then you just take the derivative of that. So the derivative of cosine is negative sine. So you would just do negative sine t. Why did I put that in parentheses? Well, if the parentheses weren't there, what would it look like? It would look like subtraction, right? So it would look like pi minus, when in reality it's pi times negative sine t. So we'll, be careful with our use of parentheses a lot as these things, get more and more complicated, and then clean it up to something that's more traditional, having the entire coefficient out in front just be negative pi sine t. Okay, and the next one, which is a polynomial, which we saw yesterday, if it's a polynomial function of sorts with different terms, you take the derivative of each term individually. So y prime here, the first term is an e to the x type function. So the derivative of that is just going to be no different than the original. The derivative of e to the x is e to the x. So we have a constant out in front that we keep there. And then the derivative of e to the x is e to the x. On the second term, again, we do have a constant out in front that just stays there. The derivative of sine x is cosine x. And there I don't need the parentheses because there's no negative out in front. And you're done. That's the derivative. Okie doke. And then just applications, giving us a g of t function and asking us for its slope at a specific point, pi 7. So if you want to find its slope, you want to first find the derivative equation. So g prime of t. We have a constant out in front that's just going to stay there. And the derivative of cosine t is negative sine t. And I definitely would want to use parentheses there, and that will get cleaned up. And then how about the plus 5? How about the term there? What's the derivative of 5? 0. So anytime you have a constant, it almost just looks like it cancels. It just disappears. You would formally, and using the right language, you wouldn't say that it cancels. But technically the derivative of 5 is just 0. So when you clean this up, your derivative formula is just 2 sine t. Can you think from, before we jump into evaluating this at pi 7, can you think from a transformation standpoint why this, whether it's plus 5 or plus 7 or plus 8, doesn't affect your derivative at all? Winter, what were you going to say? Yeah. Whether you have this negative 2 cosine t shifted up 5 or down 7 or up 25, whether the negative cosine graph, which looks like this, is shifted up 5 or up 25, the slope at any given value is not changing, right? So that constant being added on, which is just a shift up or down, isn't changing that the slope is 0 here. If you move it up 25, the slope is still going to be 0 right there. Does that make sense? Was that kind of what you were trying to say, Jalen? Josh, or were you going someplace else as well? That's the idea. Okay, good. So now on this one, just evaluating the slope at pi. So we're technically finding g prime of pi. So that's 2 sine pi. What's the sine of pi? 0. So 2 times 0 is 0. So the derivative or the slope of this function at pi is 0. Why don't, okay, so if we look at this graph, negative 2 cosine of t plus 5. Let me grab a calculator. This is all good stuff. Why don't we use the 7 for anything? Let me plot this. Negative 2 cosine t plus 5 my mode needs to be radians. Window, I'm dealing with a point pi 7, so I'll go negative 2 pi to 2 pi, and I'll count by pi's just to, let's go negative 20 to 20. Okay, so there's my negative cosine graph shifted up 5 units. Now, the point pi 7 has to obviously be on the curve, right? And if you plugged in pi here, you would see that the output is 7, but just for the sake of doing it quicker on our calculator, the point pi 7, if I plug in pi, is on the curve. Yes? We're looking for just the slope at that location. So if you look at your derivative formula, with g prime of t equals 2 sine t, you really only need to tell the equation where, at what x coordinate, essentially. Where on my graph am I looking for the slope, and it's when our x coordinate is pi. So we found that our slope at pi, that happens to be at a maximum, which is why we got a slope of 0. So because your derivative formula uses only your x coordinate to determine where is it that I'm looking for the slope, you only use the x coordinate of the point. Does that make sense? Okay. We will get to stuff where, like, maybe not a circle, but an oval, where we'll be looking for the slope anywhere on this oval. Now, if you tell this derivative that, let's just pretend it looks like this, and that's at 3. Actually, let me do something that's out here. And I know, we're going to derive things that aren't functions eventually. So if you tell your slope formula, oh, I want to know what the slope of this is at 4, well, now the y-coordinate is going to matter. Because the slope at 4, if you're talking about this point, is going to be negative. You all agree that? But the slope at this point of 4 would be positive. So your derivative formula will actually call for the x-coordinate and the y-coordinate to be plugged in. And so if this is the 0.45 versus this being the 0.43, if you want the slope up here, you'd have to plug in a 4 for x and a 5 for y. Yes, in this particular picture, but we'll have other random shapes where that won't necessarily be the case. Okay? So your derivative formulas will eventually involve x coordinates and y coordinates if the original function isn't a function, technically, right? If the original equation is not a function, fails the vertical line test, you will need to call on the y coordinate as well. Does that make sense? Okay. But right now our derivatives, because our originals are functions, right now our derivatives only need the x coordinate. More applications. Same types of applications you've been doing, so that's not really the new skill. It's just now that knowing these derivative shortcuts really quickens things up. So write an equation of a line tangent to this graph at this point. So whatever this graph looks like, here's a point on it. So if we're writing the equation of the tangent line, this is already the point we're going to use. And we just need to know what slope we're going to use. And so we need to find the slope at that point. So we first need to derive the function. The derivative of sine is cosine plus the derivative of e to the variable remains e to the variable. So it's 1/2 e to the t still. So now we're going to evaluate that derivative at the point of tangency, which is at pi. So we get the cosine of pi plus 1/2 e to the pi power. What's the cosine of pi? -1. Are you with me here? Because the cosine of 0 is 1. So when you get over here, the cosine of pi is -1. Plus, you have to live with that. -1 plus 1/2 e to the pi. So there's your slope. Not a nice single numerical value. right? Negative 1, that would be ugly. I'm just going to prove it to you. Negative 1 plus 0.5 e to the pi power. Not a pretty slope, but at least now we can see the somewhat magnitude of it, 10.57. But we're going to use that, and then writing the equation of the tangent line would be y minus the y-coordinate of our point equals your slope, and then x minus your pi. And I would be willing to bet that the answer in the back of the book would just leave it there. It's not going to go through the process of turning something like this into y equals mx plus b. Okay? But if the version that you have does look different than the answer in the back of the book, spend some time and make sure you understand how one form could simplify into the other, and try to work it out until you reach that target. Again, most of yours are going to be your test questions are going to be multiple choice. So you want to get used to having to manipulate a little bit in search of a target answer. This one's fairly ugly. I don't think I can think of any multiple choice that I've seen this gross with a slope that ugly. So I would say not likely. Now this section wants to determine the points at which the function has a horizontal tangent line versus a vertical tangent line. So we'll do two things with each of these. Starting with a horizontal tangent line. What do you know about the slope of a function if the tangent line there is horizontal? 0, right? Horizontal lines have a slope of 0. So we are going to go backwards in trying to find this point of tangency that would make the horizontal line. So if we find our derivative, what's the derivative of x? 1, right? Just the coefficient. Are we used to that? Plus, what's the derivative of 4e to the x? 4e to the x. Just FYI, so you know this too. I've also chosen like the more complicated ones that you're going to see on your homework for class purposes. So there are definitely simpler versions of these. So there's your derivative. Our derivative, since we're looking for the horizontal tangent line location, needs to be set equal to, our slope needs to get set equal to 0. So then we're going to solve that. Subtract 1 from both sides. Divide 4 on both sides. How do we solve this? ln. So x equals the natural log of negative 1/4. What do you make of that? Right. That value is undefined. So there is no location on this graph that has a slope of 0, and therefore will not have a horizontal tangent line. Now we obviously have no clue what that graph looks like, but just for visual confirmation, to round out our understanding of all this, I'm going to graph it. Okay, so it's obviously looks like to be like it's increasing infinitely. Yes? No, can we all agree? No place does it look like. Now I'm only looking at negative 10 to 10, but if I went, well, it looks like I can go a lot further on my x, but my y needs to go way up. Oh, I could have gone down further too. Window, negative 50. It does sound weird. But yeah, no places have a slope of 0. Okay? Hopefully this one will have a place with a slope of 0. So this derivative, yeah. I'm gonna do the two horizontals first, and then I'll come back to the vertical. because I want to get an x value, so then you know what to do with it. Because, well, let's talk about it. Let's pretend we did get an x value. Let's say it was x equals 5. Have we yet determined the point? No. But if we know the x coordinate is 5, how do you find the y coordinate? Plug the x back into what? The original or the derivative? The original, right? Because we're looking for the point on the original function. So that tends to be a point of confusion. You get x equals 5. Now where do I plug that 5 back in? Well, if you're looking for the point on the original function, then you plug 5 back into the original function. If you're looking for the slope at 5, then you would plug 5 back into the derivative. So you have to be aware of, what you're doing in the grand scheme of things. It's easy to get lost in the calculation and then lose your orientation in the overall problem. Where was I? What was I doing again? So make sure you think about that. Hopefully this one will give us an x coordinate that we can work with. This one, being a trig function, is a cyclical function, right? So there could be an infinite number of places that it has a horizontal tangent line. Are you with me there? So what you'll see with a lot of trigs is that it will say specifically on the interval, just looking at the graph between 0 and 2 pi. Where, if anywhere, is there a horizontal tangent line? So that's the reason on trigs where you oftentimes get a limited domain. They want to look at a limited section of the graph because it's cyclical. And if you did it infinitely, there would be an infinite number of places that it has a horizontal tangent line. So we'll think about that when we're coming up with our answer. But for the moment, the derivative is root 3. And what's the derivative of cosine? Negative sine. So you'll get better at this. That'll immediately, you can do plus 2 times negative sine, but then you get used to that's going to, turn the plus into a minus when you simplify it out. So there's our derivative. When does it equal 0? So set this equal to 0 for a horizontal tangent line. Solve it, so I'll add 2 sine x to both sides. Divide by 2. So we're looking for when the sine of x equals root 3 over 2, only limited to the interval 0 to 2 pi. So if you think about your unit circle, first of all, sine is positive, so there's an answer in the first quadrant. If you're only going from 0 to 2 pi and want that kind of relating to one rotation around the unit circle, there's 2 answers. One in quadrant 1, one in quadrant 2. What's the reference angle? Root 3 over 2. So sine of 0 is 0. Sine of 30 is 1/2. Sine of 45 is root 2 over 2. Sine of 60 is root 3 over 2. Whoops, sorry. So sine of 0, 30, 45, 60. So 60 degrees is the reference angle, which in radians is pi over 3. Okay? So x could equal pi over 3, or x could equal what would be the second quadrant version of that, 2 pi over 3. So there are 2 locations, 2 points at which that happens. Now, again, just to round out your understanding, square root of 3x, I'm just going to graph this. And window, I'm only looking 0 to 2 pi, so that's nice and easy. Make my scale just pi. And I don't know what the y coordinates are going to be, but let's just start there. Okay, so here I am looking at my original function from 0 to 2 pi. Do you agree that there are 2 locations where we have a horizontal tangent line? Right there. Which x coordinate is that probably? Definitely pi over 3. And this one? 2 pi over 3. And then it doesn't happen. I kind of lost the top of this, so I'm going to make my window go up to 10. Gosh, that kind of looks like it's about to happen again, doesn't it? I'm going to look more at that in a second. But we'll start with those two. We need the full points. So again, this is pi over 3 comma what? To figure out the actual point, because that's what it looked like, or was looking for, we got to plug it back into the original. So if I plug pi over 3 back in, root 3 times pi over 3 plus 2 cosine of pi over 3. This is going to give me my y coordinate. That number I'm never going to come up with an exact value for, so I'm just going to leave that as pi root 3 over 3. Probably more accurate. And then the cosine of pi over 3 is 1/2 times 2 is 1. So that's the y coordinate. So your point would be pi over 3, comma pi root 3 over 3 plus 1. Now, just to check on our calculator, I'm going to look at what that decimal version is, and then I'm also going to trace on my calculator. So second trace value, I'm going to plug in a pi over 3. Should be around 2.77, right? Oh, this is weird. Oh, I typed it in wrong. You see how I typed in the function wrong? That x is, no wonder this is looking funny. That x is not supposed to be under the radical when I'm typing it in. Right? Isn't that root 3 out in front? So that's probably why it was looking like it shouldn't have. Root 3x. Okay, here's our graph. Well, that's quite a bit different. And again, I still need more y space to see the whole thing, but I'm pretty confident it's not. So this is kind of funny because it looks like a flat line the entire time, but if I zoomed in there, obviously I would probably see a little more detail and that it's not a flat line the whole time. So do you mind if I zoom in just between 0 and pi, knowing that it's clearly not a zero slope anytime thereafter? So if I zoom in and just go from 0 to pi and let my values go from 0 to, I think 10 would be enough. 5 would probably be enough, but still looks flat. Oh, but you see how it turned around slightly and then goes back up? So there's going to be a relative maximum somewhere and a relative minimum somewhere in that little fluctuation. So again, second trace, now I've got it. Do my pi over 3. 2.81-ish is the decimal. So we should just, we'll confirm that that is going to give us 2.81-ish. Pi root 3 over 3 plus 1, 2.81. Okay, so I just used my calculator to prove that we actually got the right answer. So that would be one point. The other point would be from plugging in a 2 pi over 3, which when we do that, where's my function? Y equals root 3 times 2 pi over 3 plus 2 times the cosine of 2 pi over 3. So again, with that first one, we're not going to be able to do much with it. 2 pi root 3 over 3. What's the cosine of 2 pi over 3? Negative a half, right? Agreed? We're in the second quadrant, so the cosine is negative. So negative a half times 2 would be minus 1. So there's your y coordinate of the second point. And again, to check that on our calculator, second trace, and we'll look for the value at 2 pi over 3. It puts us at our relative minimum, 2.6275, so 2.62. We'll look for those to be our first couple digits. So 2.62, I'm going to remember that, 2 pi root 3 divided by 3 minus 1, 2.627. Okay? So, again, keep in mind, I'm grabbing the uglier, more difficult ones from your homework. Now, a horizontal or a vertical tangent line. What do you know about the slope of a curve if it has a vertical tangent line at that point? It's undefined. So we would try to figure out on this derivative, is there any x value that's going to lead to an undefined? No. We have no domain issues with something that's exponential like this. So this has equals undefined. And then you would just say does not exist, really. There are no places where we have a vertical tangent on this one because there are no places that would make this undefined, no x values. How about on this derivative? Any place where this would be undefined? No. No x value would be a problem there. So we have no vertical tangents there. Shoot, I wish I had an example of one. And we're not going to have tangents involved yet because we don't know the derivative of tangent yet. But moving forward, we will have opportunities for undefined. If there was ever anything in the denominator in your derivative, you would have potential for that. So that's the end of our notes, but no, we have a couple minutes, so I'm going to search for one that would lead to a vertical tangent. Yeah, I picked the ugliest ones I could find. So here's one. F of x equals 2 over the 4th root of x cubed. Well, no, we have to find the derivative first. So this function first can be rewritten as 2 over x to the 3/4. With me there? Which is 2 times x to the negative 3/4. Now we can use the power rule. Bring your negative 3/4 out in front. That's going to be negative 6/4 x to the, and this subtract 1, in other words, subtract 4/4 would make negative 7/4. Yes? Clean back up would be negative 3/2, and then x to the 7/4 would be brought to the denominator. So when would this be undefined? So negative 3 over 2x to the 7/4, when would that equal does not exist? Right, x would have when x is 0. So if we look at this function, there is probably a vertical kind of little thing right at x equals 0. You follow? When would this derivative have a horizontal tangent line? Or when would this function have a horizontal tangent line? Set the derivative equal to 0. When will this derivative ever equal 0? Never. Your fraction can't equal 0 unless the numerator is 0, and that numerator doesn't have a variable in it. That numerator is always going to be negative 3. So this function has no horizontal tangent line, but when I show it to you in a moment, we should see a vertical tangent line at 0, which I think I need to go up further. You can kind of see it happening though, how it's getting more and more vertical at the y-axis. Window, let's go up to 20 and just go negative 5 to 5 and see what happens. So what do you notice about that graph? I actually pulled this example from a section that did not have this same set of directions, so something's happening here. What does it look like is happening on your original function at 0? What do we have here? An asymptote. Can you confirm based on the look of the function that that's an asymptote? Yes. The function doesn't even exist at 0. So actually the reason that our derivative didn't exist wasn't because we had a vertical tangent line. The derivative didn't exist because the function doesn't exist there. Yes? So I pulled this from a section that wasn't really asking about vertical tangents, which is why that little glitch happened. Have no fear. If you don't follow it by tomorrow on the right types of functions, we'll get a better example. That was good for its own reason. Kind of highlights a little glitch that we will run into more as we move forward. That was a little premature though. Sorry. Don't let it stress you out. Don't lose sleep over it, Taylor. Okay. Yeah, you look okay. Hey, Connor.